Okay. Um, Hello, everyone. Welcome to the another session of book club design, and we are discussing about data-intensive applications. And from the last few sessions, we have been discussing about consistency and consensus. So today we will continue our discussion of fault-tolerant consensus. Uh, we had to discuss what are the problems with the consensus. So we will discuss that, and then we will discuss about some membership and coordination services, and mainly we will focus on Zookeeper, and then we will discuss that actually how we can use Zookeeper in various scenarios, like if you want to do leader election, or if you want to take a distributed lock, how Zookeeper can be used. And then if we have time, we will also see a demo of how we can actually do that. Okay, so 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 limitations of consensus, right? This was a topic uh, which we have to continue. Uh, so before we begin, just to revise what we did last time, I'll start with a question. So what is the difference between consensus and when we say fault tolerant consensus? So basically, uh, in consensus means that everyone should come to an agreement, and that agreement, coming to an agreement, having a consensus could be done in various ways. Like if we have multiple nodes, then a system administrator could decide that who is the leader, right? And then that leader will take all the rights, and that will accept the rights, and then synchronously or asynchronously send it to all the followers. In this case also, our system is in consensus uh, because whatever leader decides, that's the decision. But in this case, if the leader fails, then our our system does not know what to do, and then the system administrator has to step in and then choose a new leader. So while the leader is down, while there is a fault in the system, then our system will stop working and we would not be able to take any request. Whereas when we develop this fault tolerant consensus, by fault tolerant consensus, we are saying that even if there is a fault in the system, as long as majority of the nodes are working, we can still serve the request and we can still reach the consensus. And for that, we have discussed some protocol like Raft, right? And there are some other protocol like Raft, Paxos, SAB, uh, in which even if your leader dies, the system will automatically elect a new leader, and then the system will reach consensus and keep on serving your request. So that's the fault tolerant consensus. So here, the limitations that we are discussing, they are about the fault tolerant consensus. So the first limitation of fault tolerant consensus is uh, that basically to reach an agreement, right? You have to talk to all the nodes and then decide that whether what is the decision, and talking to those nodes happens synchronously, right? So that's one thing, that the process of voting on proposals is a synchronous replication, and we know that synchronous is expensive, right? So that's one thing that we need to take care of when dealing with consensus. The other thing is consensus needs quorum, and quorum needs strict majority. So that's another thing that is about consensus that might not be suitable in all situations. Then uh, continuing this discussion, so consensus requires majority, right? And in a system, to know what is the majority, I should know what is the total number of nodes, so that I know that this is the majority. So basically, most of these consensus algorithms assume fixed number of nodes so that they can take these decisions that when they have reached the consensus or not. Although, like, yeah, we could implement uh, the functionality of adding or removing the nodes, new nodes in the system, but that makes it a little more complex and you need little more effort to do that. Uh, then the other thing is that consensus rely on timeout to detect whether a node is working or it has failed. And the thing with timeout is that if your system of nodes is geographically distributed on which you want to take consensus, then there could be a large delay in the network, and you could wrongly detect that a node is down, right? And then the fifth problem is that sometimes consensus algorithms are particularly sensitive to network problems. And like in the case of Raft, there has been some edge cases where the leader keep on switching between two different nodes. Uh, and if you guys remember last time we discussed that scenario where like two nodes, they were not able to talk to each other, but they were able to talk to the other nodes in the network, then the leadership will keep on switching between them. So these kind of problems can happen. Yeah, so I think, yeah, that's it in consensus that was mentioned in the book. Is there anything else to add, or then we can move to Zookeeper and membership and coordination services? Okay, so let's now begin our discussion of uh, membership and coordination services. So, uh, when we are building these distributed systems, there are a lot of scenarios. Like if you are working on system design, that uh, we need someone to store the membership and someone to coordinate all our services. So we need to store that configuration, and we will discuss that configuration could be various things, but we need someone to store that configuration reliably, right? And so basically, there are various services built for that. Some example are Zookeeper and etcd. Zookeeper is by Apache, and so basically these are just distributed key value stores, right? And uh, again, they can be used to store those coordination and configuration service. So, and API of these services just look like the DB which supports key value stores, right? So before we continue our discussion of Zookeeper, like I had some questions in my mind, so let's discuss these questions. If people have answer, we can discuss the answers. Else, let's read more about it, discuss more about it, and then come back to these questions. Okay. So, so we said that Zookeeper, it is it is a distributed key value store, right? And we also have various databases like Cassandra is also a distributed key value store, right? So what makes Zookeeper different from these key value store database? Why do you need a service like Zookeeper? Why can't you just use that database that has similar functionality, right? So that is the first question. Then, uh, does anyone has any answers? Why would we need? Why can't we use a database which supports key value storage, similar to Zookeeper.
So, Zookeeper, in addition to storing the key value services as a key values as a database, it also gives many functionalities, right? So, like you can set watches, and I mean, you can register for events and all that. With
Mhm.
the database, we cannot.
Yeah. Okay. Yeah. Yeah. That makes sense. Yeah.
I mean, it is from the software perspective, but I don't know, like, what is the theory, like, how, I mean, why they are different.
Yeah. That's one thing. Yeah. That Zookeeper has these other functionalities, and the other thing is that like mm, many of these databases, they are designed to be highly available, and consistency is they have weak consistency uh, methods. But in Zookeeper, like we if there are scenarios like where we need strong consistency, where we need that whatever information is stored, it should be strongly consistent, then Zookeeper can achieve that. Like and although then there could be databases also which could uh, store, like which could be like HBase is a database which is strongly consistent key value store. But the point is, uh, Zookeeper is basically designed to store that small kind of config information which is dependent on, which many services are dependent on, and that information is stored in memory. So that's why it's very fast. So like basically whenever you have these kind of requirements that most of my services need to talk to something to actually decide what to do. So in scenarios like if your data is sharded in various partitions, and now you need to know that this partition belongs to which group of nodes, then that kind of config information, one thing is that most of your services will need to know this information, right? Most of your requests will need to know this information. So that means that this information should be able to be retrieved very fast, because like every request will have to first know this information. So that's why the other thing about Zookeeper is because it stores everything in memory, like it's very fast, and then you can store this key value stores uh, in strongly consistent way, right? So uh, and then as you said, like besides the key value store, it also provides these other functionalities which makes it just doing a lot of things very easily. And we will see with the example that how the combination of storing the key value store and the other functionalities like adding watches and ephemeral nodes, how it makes working with Zookeeper and building something so easily, right? uh, so then the other thing was that if Zookeeper will be used for such critical configuration services like data belongs to which partition and which node, does all request go through Zookeeper node? Will all the requests first have to talk to Zookeeper to find out what is the partition? Uh, so anyone has any answers about this?
I think like, so I don't know I think every request shouldn't have to talk. I mean, every incoming question or query need not have to talk with Zookeeper, and this is like being handled by a database in the background.
Mm-hmm.
So whatever the configuration is on the database side, that will be talking to the Zookeeper at a fairly regular interval, and that will be used to decide which node can take like, for example, if it's a read write replicas, sorry, write and master and follower architecture, then in that case, the Zookeeper will be used by the internal database code, which will be deciding who is the master and who is this secondary at any point of time.
Mhm. Yeah, yeah, that's right. Like, I mean, as long as there is a master in this system, then then no one needs to talk to Zookeeper. Like internally, databases will talk to Zookeeper uh, to set some configuration and stuff, and then the clients will talk to then this database. And right, so Zookeeper is something that these databases will have to use internally to make some critical decisions which cannot be wrong, like which should be strongly consistent. And then yeah, uh, and then like we need to talk to these databases because these databases will be handling our request. uh, so then the other question I had in my mind is Zookeeper only used to build strongly consistent systems?
As I, as far as far as I know, please correct me if I'm wrong. Yeah, Zookeeper does not provide strong consistency read after write by default. It just provides sequential consistency in case of read after write, because it's in case of read request, uh,
Mhm.
it can it can it can read data locally from not from leader node but from replica. But there is possibility to achieve strong consistency if we use sync operation before our read operation.
Yeah, you're right. So uh, yeah, so basically your rights will be handled by master, right? And so those will be strongly consistent, but reads, they can also happen from follower nodes. And so while the Zookeeper is replicating, you could read the stale values. So
Yeah,
in those cases, your read will not be strongly consistent. But if you need, like, if your requirement is that your read should be strongly consistent, then you can use sync, like you can add sync call, in which case, like, you will read from the leader, and in that case you will get strongly consistent value. So yeah, that's right. That so but like I believe that that makes it strongly consistent in the way that if you need to read if you need to read the most up to date value, you have the ability to read that, right?
yeah, I agree. As I understand, they give us they give us possibility to trade performance over consistency.
Yeah,
Or
right, right.
consistency, yeah.
Mhm. Okay, and then okay, so Zookeeper is used for service discovery, right? So does service discovery require consensus? Uh,
Maybe if like there's a network partition and you want to get a node, then which one you want to redirect to? Like if there are multiple partitions in the network.
yeah, there are multiple, and if there is a failure, then you need to know. But does knowing who to redirect to, does that require consensus? Like, uh, so we will discuss more about service discovery, but I don't believe that we require consensus because uh, basically,
Actually, yeah, agreed. I mean, like, sorry, agreed in the sense like it's not a necessity condition to build a service discovery system, but yeah, means in case you want to redirect it with minimal error, probably you want a consensus.
yeah,
But
right.
again,
So
that can make sense. Means that is again, I understand that might be make more sense in the system which we are trying to discover through Zookeeper to keep it there. Probably, yeah, that makes sense.
mhm. Yes, so yeah, so as you said, like I was also thinking this same, that yeah, it's good to have like most up to date information, that which so basically service discovery is that a system which tells you that what node to connect to get this data, right? And like if we have the most up to date and correct information, that's great, right? Because then we are redirecting the request to the right partition. But even if we have like a stale data over there and we are redirecting to the partition that is no longer available or something, then internally we can build this systems which can then redirect to other nodes. So let's say a service was hosted in 5 nodes, right? And then your service discovery says that you can connect to these 5 nodes to serve the request. Then if that information is a bit stale and right now only 4 nodes are up, that's fine, right? Then we will redirect to other node, because even if that information was most up to date, while you picked one of the nodes from that, in that duration that node could have gone down, right? So anyways, you cannot guarantee that this service discovery, whatever service discovery is saying that this node is available, that will be definitely available, right? So that's why that is something which does not require consensus. But again, as we have discussed, because Zookeeper provide these bunch of APIs other than uh, this storing key value pairs like watches and all, which makes building these things super easy, and that's why uh, we can use Zookeeper for those things, right? And so Zookeeper could be easily installed on, like, I was playing with it, like it can be easily installed on your machine. You can download it from Apache website, right? And basically, like as we have discussed, that as an application developer, we would not maybe need to use Zookeeper directly, but it is used by databases and other internal systems like Kafka and all, to make those critical decisions in this service, and that's why they use Zookeeper. So Zookeeper holds the small amount of data that can entirely fit in memory. Uh, and so Zookeeper implements total order broadcast. We have discussed about total order broadcast. So Zookeeper implements total order broadcast and consensus, along with some of more extra features. And those extra features are like, so linearizable atomic operation, right? That is one feature. Then the other thing is it can provide total ordering of operations. So basically, Zookeeper has this functionality where it you can ask for a monotonically increasing transaction ID, and with monotonically increasing transaction ID, you can always see the order of your operations. The operation which the higher transaction ID is the one which happened later before the one which has lower transaction ID. So that's how Zookeeper will provide total ordering of operations. Uh, Zookeeper can provide you ability to detect if a node has failed, and that happens through ephemeral nodes, in which case, uh, when you create a node in the Zookeeper, then you register yourself as a ephemeral node, and as long as your session lives, that node is alive. But if the session dies, then the ephemeral node is removed from from the Zookeeper. So, and your session will be dead, like if you are not able to connect to Zookeeper, if your connection breaks from Zookeepers, and in that case, Zookeeper will know that like you have failed, and it will remove that node. Then the other thing is Zookeeper provide the ability for change notification in the form of watches, right? Which will notify you, so you can uh, register to be notified when the data of some particular key changes, and in that case you will get the notification, right? So basically, then, so this is little bit outside the book, but as today we will see a demo of Zookeeper, so these things will be a little helpful. So basically, in Zookeeper, uh, so you will have a server, like right, server is a group of nodes that is hosting, that are acting as a Zookeeper server, and they are storing your key value store, right? So that is those server nodes. So that group of nodes is called ensemble. So these are these servers hosting Zookeeper, and all the nodes in the ensemble replicate the same data. They store this data in memory, right? And it has a leader and of followers. Then the clients who wants to manipulate, read and write this data, they can connect to any node, right? uh, but if your request is a write request, then although you can, so basically in an ensemble you will have leader and followers, right? So if you want to make a write request, you can connect to any node in the ensemble, but if that node is a follower, it will first send your request to the leader, and then leader will like start the consensus, and then your request will be finally served. Whereas read can be performed from followers, right? And so because the read can be performed from followers, there could be situations in which you can read the stale data. But again, as we have discussed, but if you want to read the most up-to-date information, there is a sync method which lets you do that, right? But even without the sync call, at least Zookeeper ensures that the reads will be seen in order. So there won't be those situations where you can go back in time. That kind of thing will not happen, right? Uh, so then Zookeeper has this Z nodes. So basically, these Z nodes are the data that you create in the Zookeeper database, right? So that database is a key value store. So those key values are those Z nodes. So it's a byte array, which because you need everything is stored in memory, it's a small information, so it is recommended that it should not be very large. Each Z node is time stamped, and each Z node is independent. And Suzuki, these Z nodes have something called access control list, and these access control lists are not inherited to its children. Each of them is versioned. Then each Z node could have 0 or more children. So then it behaves like a file system kind of a thing, where you can create a key value Z node, right? And inside that, you could create more of those. So you could create children of those Z node. So that is something that you can do. Then you can create persistent and session ephemeral Z nodes, right? And then you can also create counting Z nodes, which will give you monotonically increasing sequence number to those Z nodes, right? Then a formal definition: a session is a connection between a client and a node in a ensemble, right? And then these ephemeral nodes, they live and die with the session. So if you create an ephemeral Z node, as long as your session is there, that node will exist. Once your session dies, then the node will no longer be, the node will automatically be deleted by Zookeeper. And we will all see that in the demo, which we will be doing in a few minutes. Uh, then the other functionality of Zookeeper Watch, right? So Watch is a one-time trigger that you can apply on a Z node. Uh, so you can apply a trigger on a Z node, and then if the value changes, then that client will be notified. So as a client, uh, let's probably draw a few stuff and then we can understand.
I have one question, like regarding your earlier question, can we use Zookeeper as a database? So
Mhm.
if we Zookeeper can manage key value, so can we use it as a cache? Will it fit the requirement of a cache or not?
Can we use Zookeeper as a cache?
I think the problem with that one is we cannot set up other custom things like when to expire a node or all those things. I'm not sure if it has it also provides a TTL or something like that. Abhishek, do you know?
Uh, yeah, even I also don't know if it has some functionality like TTL, mm, but we could implement like we could probably implement a system on it, right? Because I was thinking that it has timestamps associated, so we can build a system on top of it which can remove the nodes if they are older than some timestamp. So I mean,
And
like, logically, it seems that we could use. I don't know what. Uh,
And what I think is if our data is like persistent, like it means like it we don't have to evict anything from the cache. I mean, we put it something in cache and it's gonna stay there for a long period of time. That is
mm,
fine because in Zookeeper design, if I remember correctly, they say that you should be. I mean, Zookeeper is good for a read heavy load, like it can take a lot of reads, but if you make it write heavy, it is going to slow down because everything is sequential, right? So
everything goes through the leader. Yeah, yeah.
yeah,
Mhm.
if you
What
make
what is the recommended size? I thought the document said 10 meg, right?
10,
1 meg, I
10
think.
kilobyte is for like a Z node, the value of the Z node.
So means
So
10K is like a
10K.
limit where it will underperform because of the huge payload and serialization issues on network transport. That, but again, like that will be the similar case with the Redis also. Like if you put a huge value with the Redis, it
mhm.
start underperforming because it's a single threaded and single thread is performing a lot of time in retrieving or writing single key. But again, the question is like means that was an interesting question. Like how do you fit a thing in a when you want to use like a system as a database? And similarly, I was thinking if it is a key value, can a key value always fit the bill of cache? Or like what are the characteristics of cache on basis of which I can say whether this system will fit my bill or not? Yeah, is my like.
Yeah, yeah. And like yeah, as I see, like in some situations it could fit, right? That if you, because basically you need to cache is also something that you need to store small information. It should be accessible quite fast. And so
So it 10K per Z node. And how many Z node we need get 10K too small, right?
yeah, so how many Zenode? I don't think they have mentioned that, and the reason could be like they have left it to you because Zookeeper is something that you will be hosting on your machine. So, and they have also let you know that the information is stored in your memory. So, based on how much memory you have in your systems, based on that, you should take the decision that how much data you want to store. Otherwise, like if you're storing too much information, you will see the memory overload issues, and that all depends on how much memory you have on your machine.
What is the 10K? Is that like limit of memory or
No, the per node key value pair that should be in
okay?
memory 10K only. So like it's more like a Z node data structure can store max size means it's advisable to go. It should be below 10K. But
I just saw it, Abhishek. It says like we can store in a single Z node up to 1 megabyte of data. So is the 10K, I mean, is that like a performance limit or like a recommended limit or
Yeah, yeah, I was reading somewhere on O'Reilly, and yeah, so he said it is recommended, and that's why yeah there is this sign. And so if yeah, I think if we want, we can store more information as well. But again, like these are recommendations.
okay?
So, and one thing, so we were discussing about using Zookeeper as cache, right? The other thing is that writes are expensive in Zookeeper because everything goes through the leader. So that is also something that we have to see. Like if we have, if our cache is frequently updated, then that might be a scenario which is not very suitable. But like in many situations, our cache don't get updated so frequently, and yeah, so then I see that Zookeeper could be used as cache. But still, like, I have not heard people using Zookeeper as cache, right? So probably we need to read about it, that what would
Yeah,
be the.
and Zookeeper does not have eviction policy. We cannot configure it, so it keeps everything in memory, yeah. And in case of not enough memory, we will not be able to evict some part of data from our memory. What do you
Mm,
think about this?
we can remove the nodes, right? So eviction is just removing the information, right? So we can remove the nodes.
Yeah, but we will have we will have to develop it. Yeah, we will have to write the code in order
Yeah, we
to.
have to write the code. Yeah, yeah. Mhm.
Yeah, so I think what you mentioned in, like, if you rephrase it, when there is a memory crunch, which node to remove is not automatically decided by Zookeeper.
Okay, right. Yeah. So yeah, if you use some service, like some service which is built for caching, then you will get those functionalities for free. Whereas here you would have to, yeah, write your own code and all, which is again like then building your own cache. So yeah. Okay, so basically, like let's say we have ensemble, right, which has, so which will store my information, which has like group of nodes. So let's say we have 3 nodes, and basically they can store this file structure kind of information, right? So it can store some information like z node 1, right? Then this information will be replicated in all the nodes, right? And we're talking about this, that so this is basically key and it will have some value, right? And this value, this key value should be, it's recommended that it should be all like not greater than 10 kilobytes of data. And then these could have their children, so children 1, children 2, and again this data will also be replicated in all the nodes, right? So this is acts as your server, right? And then you will have various clients. So these clients will connect to a node in a ensemble and do the read write request on the data, right? So this might probably connect to this might probably connect to this and this. And so it will have a leader and these will be followers, right? And so the write request will be redirected to the leader and the read could be done by followers, right? So that's what we discussed, right? So here basically these nodes that you're creating, right? So this client can, when it is creating a node, so let's say I create, so let's say it's initially empty, so I create a node, this client 1 creates a node, so it can say that this node is ephemeral or like permanent. So if I create a ephemeral node, then as long as I have the session with the Zookeeper server, this node will be there in the database if this connection breaks. And this connection, so basically Zookeeper will be sending heartbeats to these clients. If it is not able to connect to these clients, if then that means that client is no longer available, and then Zookeeper will automatically delete this node. Right. So that was the ephemeral node. And then the counting node is that if you create node, then it, like you can get this functionality that it will give a monotonically increasing ID. So if you create a new node, it will give ID 2 and so on. So that you know that which node was created first and which node was created later, right? Then the watch. So the functionality of watches. So let's say now we have these two nodes, node 1, node 2, then again node 1, node 2, right? And this is replicated. So as a client, so let's say client 1 created node 1 and client 2 created node 2. So as a client, I can add a watch on some data. So I can add a watch on, let's say, node 2, right? So I have added a watch on node 2. Now, once I have added a watch, when the data of this node 2 changes, like I will be notified that the data has changed, and the watch is triggered only once, and like it's sure that we will we will see the information that was updated just after adding the watch. So even before I got the notification, if there were some other changes that happened to this node, we can be ensured that we will see the first change, right? So that's this functionality of watch Zookeeper provides, right? So it is a one-time trigger, it is asynchronous, and the change is guaranteed to be seen by the client before any other data changes, right? And then there is this access control list. So access control list, it applies only to parent, it does not apply to children. And then, yeah, so Zookeeper has some list of IDs, world, auth, digest, IP. Yeah, and then it has some permissions. So basically these, I don't have much information about ACLs, but yeah, we can use ACLs in Zookeeper, right? Okay, so now let's see an interesting use case. So we will see two interesting use case of Zookeeper based on, so now we have seen what all functionalities Zookeeper provide, right? Using these functionalities, using just these functionalities, we can implement a leader election system. So basically what we mean by leader election is that, so basically now let's say this is our Zookeeper and our client is a database, right? So basically this is a database, and this database has a requirement that among my nodes I want to decide who is the leader, right? And so to do that, it needs a consensus, right? So either you can start implementing consensus on your own if you are working on this database team, right? Or you can, but it's like it's a bit hard to build a consensus, and if there is anything wrong, if there is any bug, then you can screw up your system. So that's why you will probably try to use some existing service which has reliably built this thing, right? And in this case, then you will use Zookeeper, right? So Zookeeper can help you decide a leader among these nodes. So anyone has ideas now using these functionalities, how will we uh, implement leader election through
We
Zookeeper?
can use ephemeral sequential node, and the node which with the lowest ID will belong to a leader.
Right. So yeah, perfect. So we will create ephemeral sequential nodes, and the node with the lowest ID will be the leader, right? That's, but then how, and what about failure? Like if something fails, how would we know?
Well, we can add watch.
We can add watch. Yeah, right. So exactly. So basically, so how will this system start? So initially, like some client, we will create a Z node leader election, right? So we will create a node leader election, and this will be then replicated everywhere. And now we are saying that everyone who wants to be a leader, so in this case anyone, they will they will create a subchild of this node, and then, and this child that we, those child nodes will be ephemeral nodes, increasing nodes, right? So basically client one first comes here. So client one will create its IP address, its node, and it will get a increasing ID one, right? So client one. So it creates this session. Then similarly, client two will do that. And similarly, client three will do that. Client two and client three, right? The other thing that we need to do is that, so now we also need to add a watch. And how we will use watches to detect when should I be a leader, like when can I be a considered leader. So I will add watch to a node whose ID is just lesser than mine, right? So this will add watch on client one, this will add watch on client one, right? And now, so basically to decide who is the leader, the node which has the least ID will be a leader. So in this case, client one, because it has the least ID, it will be a leader, right? So basically it will, you create a node and you see if your ID is the least. If your ID is the least, then you are the leader. If your ID is not the least, then you add a watch on the node whose ID is just lesser than you. So client one comes, he's the one whose ID is the least, so he decides he's the leader. Client two comes, he sees that I will create a node, ephemeral increasing node. My ID is not the least. There is another client whose ID is one, but I will add a watch on client one. Then client three comes, it will add a node. It is also not the least, and it will add a watch on two, right? Now, so let's say what happens in the case of failure. So up till now, my system is working fine. Client one is the master, right? And it is the leader. Now, when the client one dies, so when the client one dies, then this node will stop working, and Zookeeper will be sending heartbeats. So when the heartbeat expire, when the timeout happens, then this client one will be deleted, right? Because we created a ephemeral node. So this client one will be deleted. Now we have added, client two has added a watch on client one, right? So because the node is changed, basically delete is also a change. So client two will get a notification. So client two will get a notification that the one who was before you has been it has been deleted. And then client two can now see that whether he is the one whose ID is the least. So now he will see that his ID is the least because client one node no longer exists. So client two will be a leader, right? So like we have also done this failover. Let's say client one did not die, like client one was there, but client two died. So when client two died, because client three is has added a watch on it, so client three will get notified, right? So client three will get a notified that client two is deleted. Now, so client two is deleted. So now again, client three will check that is it the one with the least ID, but it will see no, client one already exists with the least ID. So now it will update its watch, and it will now basically now it will add watch on client one. So now because client two does not exist, so it is watching client one, right? So basically it is watching for client one to fail, as client one fails, then it will get notified again now because we have added a new watch, and then we can create client 3 as the leader, right? So like a, a good analogy is like, let's say you are standing in a line, right? These people are standing in a line, the one with the least, then with the second least, then with the third least. And like you are holding the person in front of you in the line. So you are always holding the person in front of you. As long as that person fails, right? As long as this person falls down, then you will get notified because you are holding him. As long as he falls, then you will come to know, you will see the jerk. So now because this person is dead, now you will see yourself that are you in the front of line. You will see no, I'm not in the front of line. So I will hold the person who is now in front of me. So this person is in front of me, So I will hold this person. I will add a watch on this. And so then this person is dead. You will add a watch on this. So like this.
It's interesting to discuss which property of Zookeeper have we used to implement consensus. We have just implemented consensus, yeah?
Yeah, we have implemented consensus among our
Does it mean that we use it total order broadcast in order to implement consensus? What helped us to implement consensus? What did help us to implement consensus?
I'm sorry, what did you say?
Yeah, it's interesting to understand which property of Zookeeper helped us to implement consensus. Which property did total order broadcast help us to implement consensus?
Yeah, so in this case, total order brought, like, not just total order broadcast, but we used total order broadcast as well. We also use the property of this session based nodes, and then we also use the ability of these watch to basically reach the consensus, basically to create a leader. So now, and again, the difference is consensus or fault tolerant consensus. So we can say that we use the property of total order broadcast in the Zookeeper to implement consensus, to know that which is the node with the least ID, and that is the leader. But to implement fault tolerant consensus, we used these two more properties, which is the ephemeral node property and the watches, so that even the failures were also detected, and then we could automatically create a new leader. Right? Is that correct? Or
Yeah, I agree. Yes, it's definitely good ideas that we used it. We even built fault tolerance, yeah, leader election. Yeah, it's very nice.
yeah.
So one assemble have only one leader, but we could have many assembles, right?
So like, so this Zookeeper ensemble is your data which is same. Like if you are building another ensemble, then you will not keep related data at all. Like if you have such large systems, so basically because Zookeeper is used to store small config information, so basically one ensemble should be enough to store your config information. Like,
Well, in what case we would use multiple ensemble? Because in the document, I think in the document you show that there's could be multiple leader.
multiple lead? No, I did not show a multiple leader.
Yeah, can
Like,
you go back to the document, scroll up a little bit? There's somewhere it say assemble, then yeah. Wait, oh no.
ensemble has a leader and followers. A leader.
Oh, have only one single leader. Okay.
And generally, when like we have a Zookeeper cluster at a place, what do they do is they keep these candidates, like these Zookeeper nodes, in a different areas, right? So one will be in one data center, another will be in another, the third one would be somewhere else, to have
Okay.
like redundancy in there.
So
Redundancy is fault tolerance, sorry.
these nodes, you are saying they will be placed in different regions?
uh, I don't know region. We can say data center, like
Okay.
entirely different data centers. Like, so we have two data centers and an Amazon cloud. Uh, one will be in Amazon cloud. One will be in, let's say, New York data center. Another will be somewhere else. I mean, if you and these data centers are already connected with a low latency network.
Okay, yeah, that is important. Yeah.
How the leader determine the ID of the client? if multiple of them, come to the leader at the same time. So is that like first come first?
So
and
we,
get-
yeah. So the property of this total order broadcast, right? That like everyone will be getting a increasing ID. So if multiple of one of them come, then like whoever is being served first, it will be given the lower ID, and then the others with the next ID. So if like multiple clients come that they want to create a node under leader election 0, then the one which comes first out of those concurrent, that will be given the lowest ID, and so on.
Oh, Abhishek, can I ask you a question about what seems to be a problem here?
Mhm.
In the beginning, you mentioned that client one was the leader, right? And all of a sudden he died and client two was elected the new leader.
Right.
But what if instead of a client one dying, it
Mhm.
experienced a network partition? So in fact, it's active, it's working fine,
Mhm.
but it's don't see Zookeeper or Zookeeper don't see client one. So what would happen in this case? Zookeeper would detect client one has died because from the point of view of Zookeeper, it does make a difference if the node has crashed or is a network partition.
Yeah.
And then in this case, client two would become leader while client one still believes it is the leader. Sort of a split brain, you know, how we can solve this problem.
Yeah,
Uh,
also to add what he said is like one more thing is in the another situation where one is not reachable to two and three client, but they are all reachable to Zookeeper. So
Mhm.
Zookeeper will feel like I don't want to do a new leader election, but actually there might be need.
Yeah.
And a couple of words from my side. We even have such situation at our work. We implemented leader election through Zookeeper, yeah, and and we had such situation. We had some kind of um, partition tolerant, yeah, and our process just lost connection to Zookeeper, and we had split brain because two different processes thought they are leaders, and we just decided to add one more check to Zookeeper. Each loop, let's say before our we have a loop in our process, yeah, and every time we will have to check if we are still leader, because in other case we can have split brain.
Yeah, right. Cool. So client one should be say keep pinging Zookeeper, and if he detects that Zookeeper is not visible anymore, so it's just stop being the leader and wait for something to happen, right?
Yeah, yes, it's one of option. Maybe there is another, but we implemented what which you said. Yeah.
Cool. Thank you.
and this even gets complicated in the case if the connection between the leader and the zookeeper is fine, and so when for example you start a JVM process, right, all these things would be running in different threads. So if there is a network partition, zookeeper will quickly elect a new leader, and with the approach we just discussed, the leader will know, okay, I'm not able to talk to the uh, zookeeper, so I should step down. But in some cases, like what we found is the zookeeper is running fine, the connectivity with the leader is also fine, the leader is also running, there is no GC pause or anything, the thread that talks with the zookeeper is also running fine, but the thread that is actually worker thread, like who is supposed to write to some system or talk to some system, that thread has stalled, just that thread, because there is a connectivity problem with there. In that case, like the whole system, like even though leader is uh, ideally dead, but he will still be keeping up as a leader. And that was like, it's like just implementing a leader election doesn't make our system do leader election. Like we have to handle all these things.
Means my question is like earlier we discussed, there's a network partition between zookeeper and client, leader client. But what if there's a network partition between the clients?
Zookeeper doesn't worry about that.
Okay, so in that case, client one thinks that it is a leader, but like for replication purposes internally in the DB, client one cannot replicate to client two, client three.
As
Means
long
that's
as you
fine.
can.
Zookeeper does not worry about that. But my
Yeah.
question is like, we need to worry when we are using Zookeeper as a consensus system.
As long as you can create that Z node and yours is the least one, you should be able to have that lock. I mean, you don't have any. I mean, you if you are able to create that node, you are the one holding that lock. There is no concept of. I mean, the other ones cannot be able to hold that lock, right? So
Yes, yes, yes. But that is at Zookeeper level. Like what I'm saying is, like Zookeeper have this understanding of a system that client one is a leader and it is replicating data to client two and client three, right?
yeah,
Now let's say client one is not reachable to client two, client or client three. So there's a
So
network
see,
partition between the clients, but all clients are reachable to are able to communicate with
so
Zookeeper.
this you're talking about, let's say this is the partition, right? So now your database also has this
No, no,
internal.
just remove this green from the arrow, which is indicating where the client one is interacting with Zookeeper. So there is no network partition there. So something like between client one, two, and three
Yeah,
only
so you are
somehow.
saying that this thing has broken, right?
Yeah.
Yes, yes.
So see, so basically now you have your actual clients, right? Your actual database users, which will be sending the request. So in this case, like in your clients, you will have the logic that if you're not able to replicate data to even just one node, then you cannot replicate his data, right? Because you're not able to connect to any of these nodes. Then you will
Mhm.
fail his request. So that is something that you can implement in such a way, right?
Yes, yes.
So yeah, so this thing is this thing would
So
be something.
basically, this then to implement that, it would be responsibility of client to whenever Zookeeper do a health check, they should mark unhealthy if they are not able to pass on, leaders are not able to replicate or get a minimal acknowledgement from their clients
Yeah, yeah.
or slaves.
Mhm.
Sorry.
Uh, and then
Got it.
these other great questions, which is like if the split brain problem, right? So I I still see the split brain problem in this sense that if client one was alive, but Zookeeper is not able to connect to it, so it will say it is dead, and then client two will now think that uh, he is the leader. So, and then we said that the one solution could be that so basically these clients are keep on sending heartbeats to the zookeeper, right? And then if we see that we are no longer leader now, then we will step down as a leader. But I was thinking that this process will take some time, right? Basically, uh, like my heartbeats or this thing will be at some intervals. So let's say that interval is 20 seconds or something. So during that 20 seconds, when I have not send the heartbeat, during that time I will still have a split brain, and during that time these both of these nodes will act like leader. So that is something that we have to be careful about.
One option would be, since there are replication between these clients, they are in constant talk. Maybe if client 2 takes over, becomes the leader, he sends a message to client 1 and client 3 confirming that he's now the leader. And these clients just, so client 1 just take over and stop being the leader
Mhm.
and don't need to rely on Zookeeper. That might be an option, right?
Yeah. So yeah, right. So like whenever someone says he's the leader, then he also broadcast to all the members of his network that now I am the leader. So that before actually taking over the leadership, it says that I am the leader. So that because we said these nodes can talk to each other, so at least then it will inform him that you are no longer leader, and that way we can solve the split brain problem.
Why it? I thought we use zookeeper to elect and to find the leader. Now suddenly we don't use zookeeper. We say okay, I'm the leader, and then
We are using Zookeeper as well, but this question which was asked. So let's say uh, we have these three clients, client one, client two, client three, right? And so these three clients, they are alive, but the client one, it can just not talk to Zookeeper because of network partition. Then because the session is now there is no longer session, like Zookeeper will send a heartbeat and it will see because of network partition it cannot reach client one, so it will delete this node, right? And when it will delete this node, client two will be notified that a node has been removed. So then client two will now become a leader, right? So now because he has the lead ID, and these three nodes within themselves, they are working, right? So now we have created a split brain problem where now this is also a leader and this is also a leader.
let's say suppose there's no split brain yet. Let's say because the way it watch for the node. So when client one die, client two get promoted to be leader, then how would client three now know client two is a leader?
So even in case of split brain problems, the leader will, as long as it is still connected to that previous node, it will be still the leader. Let's take the scenario. So let's say the leader is holding one of the client has acquired the lock and others are also created that sequential jet nodes. But it is still connected to that previous leader node. So as long as it's created, as long as the connection is alive, it doesn't do a delete of that Z node since it still has that connection. So it will, since there is no delete of that Z node, the client which has already acquired the lock, it will still be holding that lowest Z node. So others won't be able to acquire it, the lock.
Yeah. So basically, so yeah, so that's one thing. And like to add to this, so your question that how will other clients know they are not the leader? Uh, so basically, why? So basically, they know they are not the leader, right? Because when they first time connected to the Zookeeper, they created their Z node and they saw that their Z node is not the lowest, so they know they are not the leader. So that's it. Now, whenever there is a possibility that a follower could become a leader, then it will get notified for sure because we have added watches. So,
But the watch is only say like client two watch the client one, right? And client three watch client two.
yeah.
But now client two become the leader. And then how would the client three know that now client two become the leader?
So
because they only watch if the client two die, right?
yeah, so we don't need to know exactly who is the leader in this system. We are saying that, so basically we have one leader in the system, and the client, his write request is being sent to that leader, and these nodes, they might not know that who is the leader, but they will know if they are the leader or not. So they will know that they are the leader or follower, but yes, you are right, they will not know that like if they want to find who is the leader in the system, they can always find out. You just need to query this leader election node, and then in this leader election node you will see whoever has the latest least id, he is the leader now. But yeah, but that leader could have been updated. So yeah, they, like in that case client 3 will not have the up to date information. But in this scenario we have said that we don't need that information. If you need to have most up to date information who is the leader, you can build a system around it. Or like, yeah, in that case you would have to add more watches to do that. Or basically whenever you need to know who is the leader, you can always query the this node and find out that who is the leader.
But does the Z nodes have this information, like who created this node?
Yeah, so they have in their properties, they have the session IDs, right? Or basically the way you can design your system is, so these clients who are creating their nodes, right? So you create a node that my IP address, so my key in the key value pair, I can either in the key or in the value I can store my IP address. So in that way I will know that who actually is the client who is the leader.
So one thing is, I have a doubt around. So when clients are trying to acquire the lock, they are trying to create the Z node, right? So
Mhm.
I'm guessing they, since these are all rights and they have to go through the master itself, these connections are with the master itself, I'm guessing.
uh,
Leader, yeah.
so you are saying all of these are maintaining session to through leader? Is that what you're
Um, no, I'm asking that.
Zookeeper leader.
Yeah, zookeeper leader. So all these clients try to create a Z node, and these are nothing but writes, right? So the writes flow through the leader itself. So
Yeah.
I'm assuming, I'm not sure. I'm asking whether these connections will be maintained with the leader also.
No, so they can maintain the connection with the follower also. But then if this client is sending a write request, because it has maintained a session with the follower, and follower will see it's a write request, so it will forward it to the leader.
Okay. Follower to leader as well. Okay, sure.
Yeah, so it
But I have
will.
one question, like in the just extending this question. In that case, isn't Zookeeper should be write heavy rather than read heavy? Because anytime I want to take a log, I need to create a Z node. And what would be the case in which we always wanted to read the Z node instead of writing?
So, but how often will the nodes go and come, right? It's like in a real case scenario, it's not like every milliseconds your nodes are coming and going down, right? You will create a node whenever, or the node will be deleted when a new node enters the system or it is removed. So even the writes are also not that much
Okay, got it. So
compared
one more
to.
question.
Mhm.
Sorry, one more question. So when client 3, let's say now in this system, client 4 comes up. So
Okay.
it will go to follower or maybe zookeeper in general to
Mhm.
figure out who is my leader and will connect, then perform a connection handshake with the leader in database client 1.
So yeah, so that's what I'm saying. Like it depends on your database design. So let's say my database design is that all the writes of my database will go through leader, and then leader will send it to the followers, right? In this case, leader is talking to the followers, and followers don't need to know who is the leader, right? Just whoever is the leader, he will replicate his data to the followers. So if I'm building such kind of system, if my requirement is like this, then now if a client 4 comes, then I just will create a ephemeral node, client 4 over here, and I will see that my ID is not the least, so definitely I'm not the leader, and I will add a watch on the client 3 whose ID is less, and I'm done. So now I'm done, and I don't know who is the leader in the system. I just know that I'm not the leader, and basically now I'm registered in the system. This and it could be the scenario that the leader wants to know who all are the nodes in the system to forward the request to all those nodes to replicate the data, right? And in that case, the client, the whoever is the leader, he might need to peek in, and this is basically the other functionality which Zookeeper could be used to use it for service discovery. So basically, what all nodes are there in my system, right? So it can see that these are the nodes. So now it will see there is another node client 4. So it will now send the requests to client 4 as well to replicate the data.
Abhishek, can I ask you another question? So client 3, it is watching the Z node for client 2, right?
Right.
And client 2 also watches the Z node for client 1. Imagine the following situation. Client 1 is the leader, and client 2 dies.
Okay.
And client 3 is going to, that's watching client 2 Z node. What it's going to happen in this case? He's going to take over as a leader, or he need to go through the entire list of Z nodes in this path and check if he really can take over? How this works?
So yeah, so in this case, so this is client 1, this is client 2, right? And this is client 3, right? And I'm watching the person in front of me. So if this one dies, right, then I will get notified. So this one will get notified. So now it will check whether, yeah, so then in that case you will get notified, and you will have to look at all the nodes. So basically, if this was leader election, then these are the 3 nodes. So I will look at all the nodes, and I will see that if my ID is the least or not. So I will see that no, there is already C1 whose ID is lesser than me. So that means that is the leader. But I will also then add a watch on the node whose ID is just lesser than me. So I will add a watch on this C1, right? So, and probably if there was another node C0, then what I will do is I will see, okay, there is another node whose ID is lesser. Then I will add a watch on C1, and definitely I'm not the leader because there is the one whose ID is lesser. So that's what it will do.
Okay, thank you.
Yeah.
And basically, they are doing this for avoiding the thundering herd. Instead of everyone setting these watches on the least node, they set on whichever is just less than them, so that at a time only one watch will be triggered, rather than if everyone, like let's say there are 20 people, I'm sorry, 20 clients have created these Z nodes, and number one is right now the leader. I mean, the less which has a least value is number one, which is a leader right now. And if something happens to it and all other 19 clients have set a watch on number one, then
Yeah.
when it goes away, it's gonna create a thundering herd kind of a situation where everyone will be woken up. Okay, leader has died. Let's try to acquire it, and then everyone will, like, it will be a mess. So to avoid that, they do like this pattern.
Yeah. Yeah.
But you can set watch on whatever you want. It is just a pattern. Like you can say, okay, I don't want to set it on whichever is last. I can even set it on whichever is the smallest also.
Hmm. Yeah, I mean, yeah, other thing could be that if C1 is the leader and there is C2, C3, all of them are watching the leader, right? So this is also watching the leader and this is also watching the leader. And then in that case, if C1 dies, then both of them will be notified. So now this will see that this is the leader, and then it will also need to update that now it needs to watch C2 because this is the new leader. So that is also something, right? That whenever the leader dies, then everyone is notified that you update your watches to the new leader, and the new leader also comes to know that I am the new leader. But then the drawback is, then in case of a leader failure, you are triggering so many watches.
So all these implementation details, if you want to hide it, there is a Apache curator library for Zookeeper. So it has ready-made recipes in it, like distributed queue and this leader election and all. So you don't have to worry about what's happening, like am I the least, I am the leader right now and all that. It will be taken care of everything. Like you would be just calling one, like something like new leader election, and that's it. You will forget about it. So it's like a very few line of code to do all these, because the library takes care of all that.
Oh, nice. Okay. So this curator has this implementation of leader
Yeah.
election. Is that okay? Okay.
Yeah. So the generally they say like you don't want to do all these by yourself because this is difficult little bit, and it anything could go wrong. So this library, they call it recipes. So all these recipes are ready there, and it becomes very easy to use.
Yeah. Uh, and also, like, another thing I want to mention is, I could, like, we ran out of time. I could not give the demo. Probably we'll discuss if we need to do it next time. But when the leader dies, right? Then, so in my system, I created a 30-second heartbeat. So client 2, who was watching on the leader client 1, it got notified after 30 seconds, because so zookeepers sent a heartbeat after 30 seconds, that is this node alive or not, and this node was dead. So then it deleted the node, and then client 2 came to know. So client 2 came to know of the leader failure after 30 seconds, the heartbeat time. So that means that if you have this single master system, then your system will be down for 30 seconds, because for 30 seconds you won't be able to connect to client 1, and there is no other leader in the system, so you're down for 30 seconds.
Also, another scenario, like what if the ensemble, have network partition between the ensemble and all the client? In that case, the example cannot talk to any client, and it remove all the node, right? But then it cannot send a watch to all the client too, because there's a network partition.
Yeah, it will not be, yeah, it will not be able to send watch if there is a network partition. Yeah, that's true. But so it will try to deliver the message, and if it is not able to, then I believe, like when it comes back again, it will then deliver the message. Uh, okay, so we are out of time. So next, in the next session, are we going to do the demo for this and discuss this further, or do we want to move to next chapter? What do we want to do?
Demo would be better.
Okay, sure. Yeah. Okay, thank you, everyone.